Hi guys, so it's me again for another diary entry. It's again 5 o'clock in the morning, Wednesday morning. I had my second IM1 practical yesterday, which was Tuesday. So we started by reviewing some of the components of the ECG, which is what we've learned in the last lesson. So like the normal P wave duration, P wave height, PR interval, QRS duration, and so on and so forth. And then we moved on to discussing like sinus block. So sinus block or sinus pause and sinus arrest and the difference between the two. So sinus block is or sinus pause, I think it's called as well. It's a partial blockage in the sinoatrial nodes. So in this scenario, what we will see is a sinus beat followed by no P wave and no QRS wave, and then another sinus beat. So during that pause, the pause is it's more than 5 boxes in duration, so that's more than a second. In sinus arrest, the pause is gonna be more than 10 boxes, more than or equal to 10 boxes. And this is greater than or equal to 2 seconds pause, okay? So again, sinus pause or sinus, I think it's sinus pause or sinus block. I'm not really sure about terminology, but sinus block or sinus pause, I need to ask the lecturer next lesson actually. But the first one, it's a partial blockage, and the pause is more than 1 second, so more than 5 big boxes. And in sinus arrest, it's a much longer pause. So the pause is more than 2 seconds or more than 10 big boxes. And then after that, okay, we discussed about the 6 sinus syndrome. So in 6 sinus syndrome, we see a lot of things: bradycardia, sinus pause, sinus arrest, tachycardia. So in 6 sinus syndrome, what happens is the SA node is dysfunctional for some reason, so it doesn't beat that fast. So what happens is other areas start picking up the pace, and they start kind of taking over from the SA node. So that's why we see bradycardia, because of dysfunctional SA node. It's not sending impulses that fast. And then other areas, because there's a slow impulse, they try take over the pacing of the heart. So we get other ectopic foci that start firing much faster than the SA node, which is why we see tachycardia. So we see bradycardia, and then some followed by compensatory tachycardia. So that's 6 sinus syndrome. And then after that, we went on to talk about AV blocks. So we have first degree, second degree, and third degree. So first degree AV block, the problem here is that the PR interval is prolonged. So prolonged PR interval means it's greater than 5 small boxes, so greater than 200 milliseconds, because normal is 3 to 5 small boxes. So if it's greater, it's prolonged. And that's first degree AV block. And the second degree AV block, there's 2 types. We have Mobitz 1 and Mobitz type 2. In Mobitz 1, there's progressive prolongation of the PR interval, and then you drop a beat, you drop a QRS. So it goes longer, then you drop a beat. So it's characterized by the progressive lengthening of the PR interval until you miss a beat, and that's called a Wenckebach. So this is second degree heart block, Mobitz type 1. Mobitz type 2, on the other hand, PR interval is constant, and from the examples I've seen, PR interval is actually normal, so it's not prolonged. But the point is, PR interval is constant, and then you drop a beat. There's no prolongation, there's no lengthening with each beat. It's just constant, and then you drop a beat. So that's Mobitz type 2, second degree heart block. Third degree heart block, very interesting. So basically, the atria and ventricles, they contract they contract independently of each other. So it's like a divorced heart. So the SA node and so basically the atria and the ventricles, they contract independently of each other in their own intrinsic rates. So the atria contracts 60 to 100 beats per minute, and the ventricles less than 60 beats per minute. And the way you can detect like a third degree heart block is if you trace out the PR, the P waves, sorry, not the PR, the P waves, they would be like the same intervals throughout, and the QRS would be like the same intervals throughout as well, but there's no association between the two. So I don't know how I can show you, but like if you just measure the distance between P waves, it's gonna be constant throughout, and if you measure the distance between QRS complexes, it's gonna be the same, but there's no association between the P waves and the QRS, so there's AV dissociation. So that's third degree heart block. So I think for this, the treatment is probably a pacemaker. Let me just double check. Okay, so I was right. The treatment for third degree heart block is pacemaker. I don't know why I doubted myself because it wasn't on my notes, okay? But it makes sense if you think about it. So the next thing that we spoke about is atrial flutter and atrial fibrillation. So atrial flutter, we've learned that the rhythm typically is regular, but we don't see like true P waves. We see like capital F waves, flutter waves. They look like it's that classic sawtooth pattern, but some rhythms that we've seen in class, the QRS complexes are not regular, so you can have like, I think you can have an irregular rhythm then if that's the case. But again, the classic, they look like little tents, the the capital F waves, they're called flutter waves. They're not true P waves, so you can't really calculate like PR interval and stuff. With atrial fibrillation, there's no P wave, it's just squiggly lines and then the QRS, and then squiggly lines QRS. They are called like small F waves, fibrillatory waves. So and for this treatment, you have to use something for rate control, rhythm control, and consider anticoagulation because the patients are at high risk of stroke. After that, what did we do? So after that, we spoke about the normal, like QRS progression, I think it's called. So our lecturer kind of like drew the normal QRS progression in the chest lead, so from V1 to V6, right? So so it would make sense if I draw this, but it's gonna make the video longer and I don't have time today. So okay, V1 and V2 QRS is negative, which means that the amplitude of the S wave is higher than the amplitude of the R wave. From leads V3, so in V3, R and S can be equal. So V3 to V6, QRS is positive because the amplitude of the R wave is much greater than that of the S wave. So the progression goes like this. So from V1 to V6, the R wave gets higher and higher. So the R wave is like growing. And then the S wave is getting like less deep. Okay, so in V1, what we have is we have a small R wave and a deep S wave and no Q wave. In V2, no Q wave, the R wave gets a little bit taller and S wave gets a little bit shorter. In V3, still no Q wave, the R wave and S wave are, they can be equal. And then V4, we can start seeing a small Q wave. The R wave now becomes like bigger or higher in amplitude compared to the S wave. In V5, what happens is we can now see a Q wave, and then the R wave is the tallest compared to all the other leads. And then we can see a small S wave. In V6, we see a Q wave. The R wave can be taller or shorter than that of V5, and there's no S wave. Okay, so I think that's all that she mentioned for the normal QRS progression. So all I remember is that the R wave is getting progressively taller, and then the S wave is getting progressively shorter. And around V3, they become almost equal. And starting from V4, Q wave starts to appear. No Q wave in V1, V2, and V3 normally. And R wave is tallest in V5. That's pretty much the summary. And then we went on to discuss, what did we do? We did we did right ventricular hypertrophy and left ventricular hypertrophy. So my notes are so disorganized. So we did right ventricular hypertrophy and left ventricular hypertrophy. So right ventricular hypertrophy, what you need to look at is leads V1 and V2. So in leads V1 and V2, if there's right ventricular hypertrophy, the R wave is gonna be taller than 7 or greater than or equal to 7 millimeters in height, the R wave in V1 and in V2. So the causes of right ventricular hypertrophy can be, so the right side of the heart can be pulmonic stenosis and pulmonary hypertension. So I'm thinking what else. So right ventricular hypertrophy, what we can also see ST depression in V1 and 2, and potentially a right axis deviation. So just to summarize, right ventricular hypertrophy can be a result of a pulmonic valve stenosis or pulmonary hypertension. And in this condition, right ventricular hypertrophy, we can see three things. So we primarily look at V1 and V2, and the R wave should be greater than or equal to 7 millimeters in height. So that means 7 small boxes. And then the second thing we can see is potentially an ST depression in V1 and V2 and a right axis deviation. The next one is left ventricular hypertrophy. So in left ventricular hypertrophy, let's think about causes. So this can be caused by aortic valve stenosis or like systemic hypertension. So in left ventricular hypertrophy, we typically look at leads V5 and V6. Okay, so in leads V5 and V6, so we can use two different rules. So the first rule is we can conclude that there's left ventricular hypertrophy if the the R wave in V6 is greater than 20 millimeters in height. Okay, so and then we use the other rule, which I didn't quite get the name of this index, but we use RV5 plus SV1. So RV5 means that you calculate the amplitude of the R wave in lead V5, and you calculate the depth of the S wave in V1, and you add them up. And if the sum is greater than or equal to 35 millimeters or 35 small boxes, then that points to left ventricular hypertrophy. So again, to say that just one more time, in left ventricular hypertrophy, which can be caused by like systemic hypertension in like arterial hypertension or aortic valve stenosis. In left ventricular hypertrophy, we can use either the RV5 plus SV1 rule or just look at V6. So if you look at V6, if the R wave is greater than or equal to 20 millimeters, which is 20 small boxes, we can conclude that the person has left ventricular hypertrophy. And if we use the other rule, which is RV5 plus SV1, so we look at the height of the R wave in V5, and we add that with the depth of the S wave in lead V1. And if the sum is greater than or equal to 35 millimeters, which is 35 small boxes, then we can conclude that the person has left ventricular hypertrophy. We can also see ST depression in lead V5 and V6. So the next thing that we spoke about was bundle branch block. So bundle branch block, starting with right bundle branch block. So again, right, you look at V1, V2. In lead V1 and V2, what you're gonna see is a wide QRS, and the QRS would look something like this. So we're gonna have an RSR kind of looking wave. So the QRS would look like that, RSR, and the second R is typically wider than the first R, okay? But you're gonna see two distinct R waves, and then, so RSR, okay? And the second one, as I said, is typically wider than the first R. So in right bundle branch block, as I was saying, you look at V1, V2, and you're gonna see this kind of QRS wave, that RSR, and then you can also see ST segment depression and T-wave inversions. And if you look at leads V5, V6, and even lead 1, you may potentially see the slurring of the S wave, a slurred S wave. So just to say that again, right bundle branch block, wide QRS, look at lead V1 and V2. V1 and V2 would have RSR, this kind of wave, and then they will have ST depression and T-wave inversions. And in leads V5, V6, and even lead 1, you can see slurred S wave. The last thing we discuss is a left bundle branch block. So in left bundle branch block, again, we look at V5, V6, and QRS will be wide. So it will be wider than 3 small boxes. I forgot to say, you can have 2 different types of blocks. You could have a complete or incomplete. So incomplete block, which is not typical, the QRS is still less than 3 small boxes, so less than 0.12 seconds. In a complete block, it's wider than 3 small boxes, or wider than 0.12 seconds. So to say that again, we can have 2 types of bundle branch block, incomplete or complete. Incomplete, the QRS is still less than 3 small boxes, and in a complete bundle branch block, the QRS is wider than 3 small boxes. So with left bundle branch block, we have a wide QRS, and we look at V5, V6, and what we're gonna see is we're gonna see a notched QRS. So it would look like this. Forget about this. It would look like that. So the R wave is like notched, okay? It's like an M shape. It's different from this RSR. So it's notched. There's like 2 little peak there if you want. So that's gonna be seen in V5, V6. And we can also see ST depression in lead V5, V6. Also with left bundle branch block, we can look at lead V1 and V2 as well. If we see a Q wave there, which is always pathological because remember in the QRS progression, there's no Q wave in lead V1 and V2. So if we see deep Q waves in lead 1 and 2, that is indicative of a left bundle branch block. We can also potentially see discordance. So discordance is the ST segment and T wave is kind of in the opposite direction as the QRS complex. So the QRS complex, for instance, can be positive, and then that can be followed by ST depression and then T wave inversion. So the ST segment and the T wave direction is negative, and the QRS is positive. So that is called discordance. So that can also be present in a left bundle branch block. So to summarize, left bundle branch block, wide QRS greater than 0.3 if it's a complete block. If it's not, then it's less than 0.3. And we look at V5, V6, and what we're gonna see is a notched QRS like that. And we can also see ST depression in 5 and 6. And then if we look at V1 and V2, deep Q wave is it's always pathological. It's indicative of a left bundle branch block. And we may also see discordance, which means that the ST segment and the T wave direction is opposite of that of the QRS direction. So if QRS is positive, ST segment and T wave will be negative, and vice versa. That's discordance.